So we're going through more electric field questions. So in our first one, this is from 2017, the year I did it, and this is the one question I got wrong, actually. Yeah. So what we want to do is we want to find out what the direction of the electric field at the point P will be. Okay, so we can just break this down by looking at each of the charges, what the electric field would be if there was only one charge at a time. Okay, so if we just had one, we'll first look at the one in the top left corner. So this is the top left corner. If this positive charge was the only one there, remember that field lines would be going out from this positive charge, okay? So at point P, we can see that the electric field line will be going to the bottom right corner. So we'll call this electric field line TL for the top left, okay? And then we're going to draw in, we're going to look at the bottom left corner. So in the bottom left corner, we have another positive charge. So again, the electric field lines are just going to be emanating out, and it should be going in this direction here, right? So this is the electric field line from the bottom left corner. So bottom left, and so we'll give this arrow BL for bottom left. And we'll have a positive charge on the top right. So again, there's going to be electric field lines coming out from this positive charge. And this one here would be pointing in this direction. In the opposite direction to the one coming from the bottom left. So this is TR for top right. So you could probably guess by now that the top right and the bottom left are going to cancel each other out. So at point P, these two would cancel each other out. And then we have our last charge, our negative charge in the bottom right corner. So bottom right. And remember that electric field lines go in to negative charges. So these electric field lines will be pointing directed towards the negative charge. So at point P, it will be exerting a force directed towards the bottom right. So because the bottom left and the top right cancels out, but the one pointing towards the top left will add together. So the resultant, so the answer here is going to be option 4, okay? So you could say it cancelled out, or you could do vector addition. So you had this was the top right, and you had the one going to, so this was from the top left, and then you had the one coming from the bottom left. So this is bottom left, and then you had the one coming from the bottom right, which was also this way. So then you would join the the tail to the head. So this would be your final direction if you did vector addition. Okay, so joining tail to heads. But that's just for kind of like proof, I guess. Number 2, you have a uniform electric field as shown below. The potential difference between points A and B is 3 volts, and point B is at the higher potential. So remember I said that higher potential means that it's positive. So we've got point A and point B. Point B, so the right side is going to be more positive because it has the higher potential. So this side is positive, and that means that the left side is going to be negative, okay? And we want to find out the magnitude and the direction of the electric field. So if we know which side is positive and which side is negative, which way is the electric field going to go? Yep, to the left, right? So it's going to go from positive to negative. So we already know that our electric field is going to be directed to the left. Okay, and now what we need to do is figure out what the electric field strength will be. So the symbol for electric field strength is E, capital E. And there's a couple of equations for electric field strength. And the one that we'll use is the delta V, so the change in voltage or potential difference over the change in distance. Okay, so in our example here, it's 5 centimeters, so delta D is equal to 0.05 meters. And we know that the delta V is equal to 3 volts. So that's going to be 3 divided by 0.05. So that's going to be 60 volts per meter. Okay. So not too hard once you apply the rules. Shit. All right, so number 3. We have a capacitor made of 2 square plates. It's in a vacuum and separated by a gap of 1 millimeter. We have a potential difference of 300 volts across the plates. And again, we want to find out the magnitude and direction. So this time it's of the electric force on an electron placed in the middle of the gap, midway between the center of the plates. Okay. So what we would need to find out is the force on the charge inside an electric field. So I told you that we have a couple of equations for electric field strength. So we have E is equal to delta V over delta D. And we also have E is equal to the force over the charge. So how much force is being exerted on a charge that is in the electric field. Okay, so obviously the stronger that the electric field is, the more force it's going to exert on a charge. Okay, so that's going to tell you how strong the electric field is. So in this question here, what we want to find out is the force, and we already know, well, we can figure out what the electric field strength is going to be by using this equation. And we know what the charge is going to be because the charge is going to be the charge of an electron. All right, so we're going to find out the electric field strength. So E is equal to delta V over delta D. Our difference in potential is 300 volts. 300. And the distance between the plates is 1 millimeter, or 0.001 meters. And so that's going to be 3 times 10 to the power of 5 volts per meter. So that's the strength of the electric field. And now that we know E and we know Q, we can rearrange for the force. So force is equal to E times Q. So E is 3 times 10 to the 5. And the charge, so remember it's an electron. We know what the charge is going to be. It's going to be 1.6 times 10 to the negative 19. So it's going to be negative. It's going to be a negative charge, but because we just want to find out the magnitude, we can just use the value. So that's going to give you 4.8 times 10 to the power of negative 14 newtons. Okay. So it's going to be either option A or option B. So then how are you going to figure out whether the force is going to be upwards or downwards? So which plate? We have 2 plates here. We have the top plate and the bottom plate. We know that the top plate is 300 volts and the bottom plate is 0 volts. Which one of these plates is going to be positive? Yeah, the top one. So top is positive and the bottom is negative. Okay. And we have a negatively charged electron in the middle of this electric field. So which way will the electric force be, or which direction will the electric force be on the electron? Yep, so it's going to be up, because it's going to be attracted towards the positive plate. Okay, so your answer here is B. Okay. Number 4, we have a charge of -1 microcoulombs that's moved from point A to point B and then to point C as shown in the figure below. So here, all we're interested in is the starting position and the final position, okay? So we don't need to care about where it's gone in between. So our change in distance here is going to be from point A to point C. So we can write down that our delta D is equal to 10 centimeters, which is 0.1 meters, okay? So what we want to do is we want to find out the work done by the electric force on the charge in millijoules. So there's 2 ways that you can do this. I'm going to show you both ways. So the first way you can find it out is to use work is equal to force times distance. So we know what the distance is. It's going to be 0.1 meters. So we need to find out what the force is going to be. Remember that if we have a charge inside an electric field and we know the electric field strength, then we can figure out what the force is going to be. So force is equal to the electric field strength E multiplied by the charge Q. So our electric field strength is 1500 times our charge, which is -1 to the power of negative 6, negative 1 times 10 to the power of negative 6. But we can just use 1 times 10 to the negative 6. Okay. And that's going to be 0.0015 newtons. So that's our force. So work is equal to force times distance. 0.0015 times 0.1. So that's going to be 1.5 times 10 to the negative 4 joules, which is equal to 0.15 millijoules. Okay, so your first option is to use work equals force times distance, and then use the electric field strength and the charge to find out what the force is going to be. And then your second way to find it out is to use the electrical energy equation. So we used this before. So the electrical energy U is equal to the charge Q multiplied by the voltage, or the potential difference that it travels through. So in this case, we need to figure out what the difference in potential is going to be. So remember, we had our equation E is equal to delta V over delta D. So what we want to find out this time is delta V. Delta V is equal to E times delta D. So that's 1500 times 0.1, which is equal to 150 volts. So it's traveled through a potential difference of 150 volts. And then we can use U is equal to QV. So U is equal to QV. And our charge is 1 times 10 to the negative 6 times 150. And that will again be 1.5 times 10 to the negative 4 joules, which is 0.15 millijoules. Okay? Yeah, and it's negative because remember that, so here the arrows are going to the right. The electric field lines are going to the right. So it means that the left side must be positive. So the left side is positive, and the right side is going to be negative. Okay, since the electric field lines are going to the right. And you've got a negative charge. A negative charge that's moved to the right. So the electric field, if the electric field was to do work on the charge, it would have moved left, because that's what the electric field wants to do, because negative charges will be attracted to the positive charge. But since it's in the opposite direction, that's why the work done is negative, right? I don't think this question is actually that accurate, because you can't really have negative energy. It would be done, the work would be done by an external force on the electric charge. But anyway. Number 5, we have a small charged oil droplet, which is suspended and stationary halfway between two metal plates, which are 10 millimeters apart. There's a uniform electric field between the plates, which has a magnitude of 2 times 10 to the power 4 volts per meter. And this electric field is directed vertically upwards. the downward gravitational force on the droplet is 6 times 10 to the negative 6 newtons. And we want to find the true statement regarding the potential difference or the voltage between the plates. Okay. So there's a few clues here which you need to recognize in order to solve this question. Okay, so first of all, we're told that the oil droplet is stationary. So that means that the net force on the oil droplet is going to be 0. So the downward force is equal the upward forces. And we know that there's a downward force of gravity, which is 6 times 10 to the negative 6 newtons. So that means that the upward electrical force must be equal to 6 times 10 to the negative 6 newtons, equal to that gravitational force, right? So here's our top plate, and here's our bottom plate, and we have our negatively charged, we don't know it. We don't know what charge it is yet. So, and we know that the field lines are directed upwards. So that means that the bottom plate must be positive, and the top plate must be negative. And if we know that there's a downward gravitational force, there must be an upward electrical force, because it has to be stationary and net force has to be 0. Okay. So that means that this charge would have to be positive in order to be attracted to the negative top plate. So what we want to find out is the potential difference, or in other words, the voltage. So the electric field strength is equal to delta V over delta D. So we know that the distance between the two plates is 10 millimeters, so delta D is equal to 0.01 meters. And the electric field strength is 2 times 10 to the power 4. So what we need to do is we need to rearrange this equation for delta V, which is equal to E times delta D. So delta V is equal to the electric field strength, which is 2 times 10 to the power 4, times delta D, which is 0.01. So that's going to be 2 times 10 to the power of 2, or 200 volts. Okay. So as the potential difference is 200 volts, and we know that so which one's going to have the higher voltage? Which plate, top or bottom? Bottom, right? So remember that the positive plate always has the higher voltage. So option B is going to be true. The potential of the top plate is 200 volts lower than the potential of the bottom plate. Okay? So it's a little bit of a hard one, but yeah. Just a few clues that you need to recognize. And then question number 6 is carrying on from that same question stem. So we want to find out what the charge is on the droplet. So we have the electric field strength for E is equal to F over Q, and we can rearrange that for the charge, so Q is equal to F over E, right? So Q is equal to the force, which is 6 times 10 to the power of negative 6. Remember, that's equal to the gravitational force. And the electric field strength is 2 times 10 to the power of 4. And that will be 3 times 10 to the power of negative 10 coulombs. And remember that we said before the electrical force must be upwards, so that means the charge would have to be positive. Okay? So it's going to be positive 3 times 10 to the negative 10 coulombs. Number 7, if a single electron was accelerated from rest through a potential difference of 50 volts, what would the final velocity be? So here we want to find out the final velocity. So it's pretty similar to that one we did in the basic tutorial, where we want to find out the kinetic energy, but this time we want to find out the final velocity, so we need to take it one step further. So the electrical energy that it will have will be equal to the kinetic energy. And the equation for electrical energy is Q times V. And the equation for kinetic energy is half mv squared. And if you rearrange this equation, you're going to get the velocity v is equal to 2 times qv over m, the square root of 2qv over m. So what we need is the charge and the voltage difference, which is 50, and we need the mass. So it's an electron, so we know what the mass and the charge is going to be. So 2 times the charge of an electron, which is 1.6 times 10 to the negative 19, times the voltage, which is 50, and the mass of an electron, that's going to be on the formula sheet that they give you. That's 9.11 times 10 to the negative 31 kilograms. And that will give you 4.2 times 10 to the power of 6 meters per second. Oh, Game of Thrones. Number 8, we have equipotential lines produced by a pair of charges. A charge of positive 2 coulombs is moved along the dotted line shown from A to C. So again, all we care about is the starting position and the final position. Okay, so it doesn't matter that it's gone to the 11 volt line. It's, as far as we care, it's gone from positive 2 volts to positive 8 volts. Okay? So it's traveled through a potential difference of 6 volts, and we want to find out how much work has to be done against the electric field in order to complete this procedure or movement. So work has to be done against the electric field, so you can just say work is a form of energy, And electrical energy U is equal to Q times V. So our charge is going to be 2, and our potential difference is going to be 6. So that's 12 volts. Oh, sorry, 12 joules, not volts. So that's energy. 12 joules of work has to be done, which is going to be equal to the amount of electrical energy that has been gained by this charge. So when I say that this charge has gained electrical energy, if you go, so remember that as you increase the voltage, as the potential becomes higher, that means that it's more positive. Okay, so the +2 voltage line is relatively negative compared to the +8 voltage line. So if you just compare the 2 points, this place will be more negative compared to this point. So if you have a positive charge, a positively charged molecule, and it moves to the right, it doesn't want to move this way, does it? So that's why you have to perform work against the electric field, right? And it's like compressing a spring. When you compress a spring, you're forcing the molecules together when they don't want to be together. It's the same for these charges. So you've got a positive charge. It doesn't want to be next. It doesn't want to go towards the positive charge. But since you've forced it there, it's going to gain electrical potential energy. Okay, so it's going to have electrical potential energy, and when that's released, that can do work. So it's a bit off topic here, but that's basically how your chemical bonds work. So when you have adenosine triphosphate, or ATP, you've got your adenosine, and then you've got your phosphate. So phosphate is negative, remember? And you've got these 3 phosphate molecules bunched up together. So these are all negative molecules that don't want to be next to each other. So it's like a loaded spring. And then when you break one of these off, that can release energy, right? And that can power whatever reaction you want to perform in the cell. Okay? So that's a pretty simplified way to think about it. But I wouldn't write that down in the exam. Number 9, our last question. The diagram below shows equipotential lines in a region where there's a uniform electric field. A proton is released from rest at the point marked with an O. Which one of the following statements best describes the motion of the proton after its release? So we have 0 volts, and then we have 3 volts over here, and the distance between them is 1 meter, and we have a charge. So we have a charge, a positive charge. So remember, protons are positively charged. So what we first need to do is we need to find out the strength of the electric field. So we can figure out the strength of the electric field by using the change in voltage over the change in distance. So the change in voltage is 3 volts over 1 meter. So that's 3. Okay. And then the force now that we know the electric field strength, we can use E is equal to F over Q, and we can rearrange that for force, which is equal to EQ. Okay, so then force is equal to the electric field strength, which is 3 times the charge. So the charge of a proton, that's on your formula sheet, that's 1.6 times 10 to the negative 19. And so that will be 4.8 times 10 to the negative 19 newtons. And then, so the options, obviously the A, B, and C are wrong because it's not going to remain stationary. And it's not going to move at a constant velocity, it's going to accelerate, so it's either going to be D or E. And we actually know that it's going to be E because it's going to move to the left, so it's going to go from, it's a positive charge, and we know that this side is positive and this side is negative, right? Because the higher voltage is always positive, more positive. And so we know that the proton would move to the left towards the negative side. So it's going to be option E, but if we want to be completely accurate and make sure that we've got the right answer, we can then find out the acceleration. So force is equal to mass times acceleration. We can rearrange for acceleration. So A is equal to F over M. The force is 4.8 times 10 to the negative 19 over the mass. So the mass of a proton, that's also given to you on the formula sheet, is 1.67 times 10 to the negative 27. And that will be 2.9 times 10 to the power of 8. Okay, which is pretty close to the speed of light. Okay, so that's the end of our advanced tutorial. We've finished pretty early, so I'll stick around for maybe 20 minutes and you guys can ask me questions if you want to. All right, cheers. Thank you.